So welcome back to our course on cyber-physical systems. We're going to continue with chapter 2 and pick up where we left off. We were talking about this diagram as a reasonably good example of a cyber-physical system to make a distinction from classic embedded systems. So if you think about a more monolithic embedded system, you have a computation element, you have actuators, you have sensors, but in this cyber-physical system, if we have a physical plant, which could be a distributed entity, it doesn't have to be all together. This just represents something that you want to control and have access to. If you have that plant, it may be that you have different physical interfaces. So that's the interface to that physical part of the system. And through those interfaces, on this side, for example, you have a sensor and you have a computational unit. So this could be a classic sort of embedded system. And then, for some reason, you have this other physical interface such that the computational unit on that part, you cannot seamlessly make a connection. And we'll make a distinction between a connection and a network. So you have this computational unit over here, and you have sensors on this side, and actually you have two computational units, and you are combining, let's say that you're doing some sensor fusing or sensor fusion, and that is driving some actuator through this physical interface. So that's a second platform, platform 2. Now, on this side, you have this other platform has one sensor, some have two interfaces with platform 2, which is through a network fabric. So we have here the output of this computational unit going into this one, and also one output of this computational unit going back into computational unit 1. So these two links are connections through a network. And when we invoke network, we're not talking about a simple connection, my connection, the one that I am interested in. A network implies more than one connection, more than my connection. So it's a number of connections, and that implies access. And that's a good thing, because many actors can take advantage of that medium. But it also introduces vulnerabilities. So security is an issue of concern in cyber-physical systems that have these computational units that are linked through network fabrics. So that's why in the context of cyber-physical systems, we're going to see that, in my mind, the idea of good systems engineering and the art of system architecting, I think is sort of an art, is being able to choose good components and good interfaces that serve the purpose of the specifications of the system according to some constraints. So it's not to use the first thing that you find available, the cheapest component, the easiest thing to use. It is the optimization, the thoughtful optimization of the system according to some constraint to meet the functionality. And that's why the development of a specification is so important, because that drives the whole quality flow of the endeavor of putting together this system together or this product. So we're going to see that in that context, standardization is very important. And we sort of take it for granted, but we are surrounded by standards. So we're going to devote a few slides, more than a few, to talk about standardization. And we're going to start and touch on some historical interfaces and see how they have evolved and help evolve some embedded systems architectures, and you'll see examples of very good well thought out system evolution. So we're going to look at standards of connectivity, communication, and also standards of embedded system platform. One specifically, we're going to spend some time on that from a historical perspective, but also as an example of something that was a good idea at the time and how it has evolved. So far, from a board level perspective, you should be very familiar, comfortable, and we have discussed your common UART two-wire protocol that is used for point-to-point type communications. Also with the SPI protocol, the serial peripheral interface, that uses 3 wires plus enable signals for each of the slaves from the master, so that the master can select which slave is the one that is going to be addressed. So it has three wires, the clock, it has a master out, slave in signal, and a master in, slave out signal. So that's the data lines. And then also we discussed the Icrc protocol, a 2-wire protocol that allows for, it was devised by Philips before some of that became NXP, and it was devised to hook up and be able to make a network of ICs on a board. So it's an addressable bus where each device has an address, and it supports of course a master-slave arrangement, but also it supports multi-master, so peer-to-peer type communications. So with that, let's think about what happens when we try to put a communication protocol together. And the simplest protocol that you can think of is some processor trying to get data from a memory, reading, or writing data to a memory. So in its simplest form, what are the minimum entities that we need in that protocol? Well, first we're gonna make the distinction of wires. So we need wires. If this is a, let's say on a board from chip to chip type protocol, we need wires. Those are single connections, and we're also going to have buses. So buses are a collection of wires. So such as a data bus or an address bus. So at a minimum, we need to be able to, the processor needs to be able to address this memory so that it can tell it which is the address of interest. And then we need also a data bus, because we need to be able to receive the data from the memory if we are reading, or providing that data to the memory if we are writing. Then we also need to be able to tell the memory, or to establish from a protocol perspective, what is it that we're doing? What is a transaction? So these are control lines or transaction lines. We must be able to specify whether we are reading, in this case, reading with the tick means read not. So if this is a 1-wire, a read would be a 0 and a write would be a 1. So with the single line, we can specify the 2 transactions. And then we may have like an enable line, an additional control signal. So this is the simplest protocol that you can think of. And of course, there is quite not such a thing, because the simplistic, we can add more intelligence to the connectivity and the protocol. The first thing that comes to mind is we can add a clock. If we add a clock, then we can synchronize these lines, and we can run at a much faster speed than we would if we didn't have that type of synchronization.
Question.
Yeah.
For the last slide, or just even here, what's that slash in the middle of the path for processor to memory on like address and data?
Very good question. So the question was, what is this slash here in that single line? So that means that it's a multi-bit or a multi-line bus. So that means in this case that that line signifies that it's really eight connections from 0 through 7, and this one would be 12. So that's what the symbology means. So data communication protocols are important, and we are communicating between ports. So in general, that's what we call how entities communicate or modules communicate with their surrounding world. If we're talking about a chip, then it could be an actual pin, or it could be a ball if you are in a BGA type package, and things of that nature. Now, let's talk about timing diagrams. If you are designing a system on a board, as I mentioned, a big part of the elegance of what you're going to do is choosing the right parts and the right interfaces. But how do you know? There's a myriad of them. The way that you know about the fitness of these parts and interfaces is through data sheets. A lot of what you're going to be doing and what you do as a system designer is reading documentation so you can then choose the right component and the right interfaces. And the communication of what these components do is communicated to you by the maker, by the manufacturer, through the functionality described in data sheets and also timing diagrams. So that's an important part of understanding how protocol and standard protocols behave. So in this case, we have two timing diagrams for the read function, for the read transaction of the protocol, and the write transaction of the protocol. So how would we read this? So we see that the address, the entity that asserts the address, is the processor. In this case, that would be considered the master or the client. It asserts the address. Then, in this protocol, there is an implication, an assumption of timing. And implicit by manufacturing, by construction, and by design, we are assured that if we present the address and wait this amount of time here, the setup, the memory, the slave or the server in this case, is going to register that address. That's the address that we're talking about. So we have to wait this time until we assert the enable. So we enable the transaction. At this point, the memory is going to have understood this address and is going to take some time to put on the bus, on the data bus, which is bidirectional in this case, the data that was at such address. How does the memory knows that that's what it needs to do? Because the read signal is low. We have specified that it's a read transaction. So that would be a read transaction on this protocol. How about a write? If we're going to do a write, we have to assert the write signal. We have to put the address where we want to write, and also the data that we want to write at that address. And we have to wait certain time, in this case saying the setup time, until all that registers at that actor, the memory in this case. Then we assert enable. So remember, the control signals like read, write, enable, these are always controlled in a client server or master slave type protocol. They are controlled by the master, in this case the processor. So at that point we assert the enable signal. There is some time that goes by. that is specified by design and construction and manufacturing of that component. And after that, we are guaranteed that the data has been written into that memory location. So at that point, we can deassert the enable signal and the transaction is complete. If for some reason, the data doesn't register at that address during that time, then the part is bad. That's a bad part. That's a defect. Okay? So that is guaranteed by design and construction. So sometimes, some of the things that get done in communication protocols is a trade-off. The trade-off of bandwidth versus simplicity or cost. Simplicity and cost are related in many ways. So let's say that we have a setup, two entities, a master and slave, and in this case, all that we need to provide from the master perspective to the slave is data, and we know where that data is going. And so simply we can serialize the data. But let's say that in this case our data is 16 bits, and we only want to spend on 8 connections. So one thing that we could do is serialize the data. We can send a byte first, and then we can send another byte. So these are trade-offs. We could have had all 16 with 16 wires, but that would be more expensive and more complex. So this is a simple example to illustrate trade-offs. Now, later on, a client or a customer comes and says, but now it's not good enough that we just send data blindly, okay? I want to send an address as well, because we were kind of encoding the address in the data, but now that's too difficult, and we just want address and data. Well, it may be unrealistic and not feasible to add an address capability. So you can look at it as an architect and say, well, we're going to multiplex the address and the data. So you could do that. You could do that on the same lines, in this case, and let's say that you have 16 bits of data, and you only have 8 wires, so you maybe sending 2 chunks of data, but now you have 24 bits of address. So maybe your scheme looks address, data. That transaction becomes a bus cycle, which may take many clock cycles. That is a bus cycle, because that's what the transaction is. You need the address and the data to affect the transaction, whether it's read or write. So that's the distinction between clock cycles and bus cycles. A bus cycle is what it takes to affect a whole transaction in a communication between two communication entities. Now, another example of protocol concepts. Let's look at a strobe protocol, and you already saw that I mentioned the guarantee by design or construction timing-based type of protocol. So let's repeat that here. Let's say I have a request and data. Here, the master asserts the request line, and by construction and design, we know that if the master waits the access time here, by that time, the slave would have put that data on the bus, and the master can get it and then deassert the request line. That's a guarantee. The master really never knows that that happened. There is no way. There is no way. It's being assumed that it happens by construction because that's the way it's designed and the part is supposed to behave that way. So in a sense, that's a weakness. Depending on your system, if you have to design a protocol that is more resilient, that you need to know that you have the right data, that the message was received, then maybe you don't rely on timing. You rely on an event-driven protocol, which is the one here on the right, and relies on a handshake. So in this case, same thing, the master is going to make a request, but it's just going to wait until the slave has an acknowledge or issues an acknowledge. And now the master knows that yes, it got my request and it put the data on the bus. So now the master has an extra assurance because he got feedback from that other entity. Then the master has time to get the data, then it deasserts the request. That is a signal for the slave to say, well, the master got it because it's deasserting the request line. And then at that point, the slave deasserts the acknowledge, so a not acknowledge or a NAC. That concept of ACK and NAC, that is using Icrc, for example. And at that point, it can basically free the bus. It frees the bus. So hopefully you can see that this is more robust, but it costs us an additional line, an additional logic, additional actions. So that's another example in sort of the basic protocol concepts realm. So as we start talking about standardization, at least this presentation here on that starts with the Pci Bus, an industry standard bus from the beginnings of the PC era. And this is the bus that was used to connect the processor to the memory and to the peripherals. So it actually it uses separate control lines for reading peripheral or reading memory. And it uses a single write. And it was a parallel bus of 16 bits of address space for I/O and 20 bits of address space for memory. So pretty similar to a memory protocol. So this is kind of where all started, as we saw a lot of growth and proliferation of electronics in the early 80s. Now that, as I give you some historical perspective, evolved into the PCI bus, or peripheral component interconnect. So that was originated by Intel in the early 90s, and it was adopted as a standard. Sometimes standards are adopted by bodies like IEEE, or sometimes special interest groups are formed, which is a collection of interested parties, not just companies. Sometimes a consortium is formed. So there are many ways for interested parties to come together and put a standard together, and if there is enough interest and if the standard is good enough, then there is wide adoption. So this started connecting many things, and with pretty good bandwidth, 127 to 500 megabits per second, and he had an address space of 32 bits. and it was expanded to 64 later on. This was an asynchronous bus, meaning that it had a clock. And it used a multiplex data and address lines that we saw a few minutes ago. So these are things that I'm sure were discussed and trade-offs were made. And this is the approach that was taken from a systems perspective. And we're going to be talking later about the evolution of PCI to PCI Express and eventually how it is gone away, except on some embedded platforms that we're going to be discussing. But today's PCs don't have PCI. It has dedicated bus as things have gotten integrated, and Intel has come up with the North Bridge, South Bridge architecture for memory and peripherals, and then everything else is kind of serial. Everything else is kind of serial. Because serial physically is very inexpensive. It's a few wires versus wires are expensive. Interconnect is expensive. Whether you're talking about chip design, board design, cabinet design, or system design, harnesses and wires are a major part of the expense of the system realization. So since semiconductors are faster and we can run at higher data rates, it's become more feasible to serialize things that were parallel before. A classic example is the evolution of parallel interfaces for disk drives to serial, from parallel to serial. So we use today nothing but serial ATA, okay? So, and again, it's less costly, but the design is more challenging. To keep the bandwidth, you have to run higher rates, and that requires, at the circuit design, a lot more know-how, because now you're running at higher rates, that data is coming, you have to be able to serialize, because inside, let's say inside the chip is parallel, you have to be able to serialize that data, send it out at very high speeds, grab it at those very high speeds, and then deserialize it. So those modules are called SERDES, serializer deserializers. So you need to know that these things exist. These days they are integrated in high performance systems like high performance FPGAs. So if you go to Xilinx and you're going to use this technology or this technique of serialization, you can pick an FPGA that has a SERDES integrated in it, because actually it's a very sophisticated piece of analog circuitry. It really, the signal, even though it's digital, since it's at such high speed, it's treated as an analog signal. There are techniques of clock recovery from the signal, so synchronization can be maintained. There is a lot. So these are sophisticated pieces of circuitry, and thanks to them, we can get rid of the wires and make things more expensive, less expensive, because we can handle the additional complexity. A good example is USB. That's for anything. USB is replacing even video cables with the latest standard USB-C. It emerged as a two rates, 1.5 and 12 megabits per second was considered the high rate, but still could not do media. So with 12 megabits per second, you still could not do handle media well. And at that point, there was a competitor. There was an IEEE serial bus, actually more sophisticated than what USB started as being, and it was called codename FireWire, but it was an IEEE standard that was strongly backed by Apple, because USB also came from Intel, strongly backed by Intel. But in the end, FireWire went away when USB reached higher speeds, because when USB was introduced, FireWire was running already at 400 megabits per second. So it had a lot to go to catch up, but it did. And that's the kind of the range that we are with USB-C these days, and more. So USB has emerged as a very widely adopted serial bus. It's a sophisticated serial bus that allows us to put together a star topology. It allows for three types of actors: a host, in this case, sort of you can envision a PC, a processor of some kind, and you also can have a hub. So a hub allows you to connect many devices to a single port on a host. So it's sort of like a bridge. So you can have hosts, hubs, and devices and form this star type topology network, and you can have up to, or initially you could have up to 127 devices. Okay? Quite sophisticated. You can enumerate, you can negotiate presence in the bus, manage bandwidth, and things of that nature. All of that is a combination of hardware. And think about what we were talking about the other day about the importance of partitioning hardware and software. How much are we going to be doing by the chip? How much are we going to be doing by the software driver? These are system level things that have been done in the past. Things that have been done in the past that are good precursors to all the technology and the advances that are coming in the future that you need to be part of. And then we also have the advent of wireless. Of course, we had radio, we had radar, we had microwave, but wireless actually, until, let's say, 30 years, 20 years ago, it was not a pervasive technology. It was there, it was very expensive. It was very expensive. And it was really limited if you want to talk about IR as a wireless type of communication to your remote control. So very limited, you require line of sight, and very inexpensive. Basically, you require a photo transistor and an LED, an IR LED, and you can have your IR communication. But then we started looking at wireless technologies. Why? Because before silicon technology became fast enough to do a lot of the circuitry for RF, and also the other RF type of semiconductor technologies became less expensive, wireless was expensive. Military used wireless, the radio companies, the broadcasters, but we didn't have a lot of access to wireless, other than maybe the 900 megahertz cordless phone was the first thing. Wasn't very good. It had a lot of interference, couldn't go through walls very well because the technology was not there. Because RF technology was not being done with the low-cost type of silicon that everybody, most of the products were using. They were using other type, not CMOS, not silicon, gallium arsenide, BiCMOS. This is much more expensive than the way things are done now because the technology has gotten faster and less expensive. So RF wireless, to make a distinction from infrared, is much better than IR. And at higher frequencies, the antennas get smaller. So that's a good thing. That's why we want to run at gigahertz and not megahertz. And power, you have a lot of flexibility on power management because you can adapt your power to the distance and the reach that you want to have.
Question.
Yeah.
So yeah, as frequencies go up and then the antennas get smaller, are we going to get to a point where the size is going to be difficult to get, I don't know how I'm trying to work with the question, but you know what I mean, how small can we go with antennas?
So the question was how small can we go with antennas? And there is nothing that says that the antenna needs to be small, okay? But there is a minimum size that you need to have. You need to have at least 1/4 of the wavelength. So we know that, but the antenna can be larger. So there is nothing that says that nothing is really pushing you to make the antenna smaller. So you make it as small as you can get away with to get reception. But you could make the antenna larger. So that limitation is not there. But you do have a minimum size. You cannot make it smaller than 1/4 of the wavelength. Just the way the reception physics on the electromagnetics physics work. So I don't think that there is a problem with that. But, okay? So as we have evolved with wireless, now we have Bluetooth. Again, this is not an IEEE standard. It emerged in Europe and made all the way. And it has opened up all kinds of markets, products, services. Is being amazing, the success of the standard. And originally came up with a connection about 10 meters, expanded to another class with a little bit more range. But now we have really this flexibility. We have industrial Bluetooth that can reach about 1 kilometer or 1/2 kilometer. And we have BLE, which is very low power, but it's really constrained to what we would call a body area network, if you will. And so technology and communication and standardization has played a big role in all the access that we have to different interfaces and different components. So, as a good example of that, let's start talking about the PC 104 embedded computing standard, which was started by the PC 104 Embedded Consortium in 92, 12 companies, including IBM. Now, by that time in 1992, the PC had started its coming for about 10 years, 10, 12 years. And it was clear that the PC was here to stay, okay? That was clear at that point. So now the idea was to come up with a standard for a embedded computing unit that could leverage what had been learned through those 12 years in the PC industry and leverage the tools, leverage the tools that have been developed for software development at that point. And we're going to go through kind of a journey and learn about the evolution of PC 104 to PC 104 Plus, the PCI for embedded, and PCI 104 Express. The 104 originally came from the number of pins in the connector. That's where the 104 comes from, just some trivia. It took 104 pins in this connector that they define physical connectivity for the system. And this is a standard of a system. This is an actual board with a specific mechanical interfaces. The holes had to be what they needed to be. The connector had to be at that point. It had to have this structure at the connector, and it was very small. As a computing platform for embedded system with the same characteristics of the PC to leverage code development that have been done for the PC for the last few years. So this was only about 4 by 4 inches in size. Okay? So that gives you another view. So this initially, and the reason that I mentioned the Pci Bus as what the PC started with is because they also started with the Pci Bus. And you can see here the 104 pin Pci Bus. That was the original. But then came PCI. Remember that PCI replaced Pci. But from a system perspective, for embedded system, remember that if you're making a monolithic PC, you can get away with getting rid of Pci and just putting PCI. And every time you sell, you're putting together a whole new system and sort of a standalone system. But as you'll see, this standard called for expandability, being able to stack any source of any type of boards like this to achieve all kinds of functionality. Because as we discussed, the system, embedded systems are heterogeneous in nature. So we had to have all kinds of boards stacked to address all kinds of systems and functionality. So there was an installed base already on the Pci side. So they did not get rid of Pci completely. They added PCI. So the second incarnation, which they call the PC 104 Plus, just added the PCI bus. And at that time, and at that point, the real estate being occupied by the connectors started getting pretty big. So that's a rendition of how the concept of stacking any number of these boards for different types of functionality and addressing different needs. So you could get complete single board PCs, then you could have expanded I/O with I/O cards, or you could have analog processing on some cards, and everything would connect up and down the stack through the bus, whether PCI or Pci. You could have communication like CAN or Profibus or Ethernet. You could have media. At the time of the usage of this would be PCMCIA cards for memory storage and media retrieval, and all kinds of other things. So it was a good evolution, and then at some point, when that consortium that monitors the industry and knows what's going on, they decide that it was enough for ISA, then they just got rid of it. Okay, but this is an example of a board that would do certain function. It would do certain function, and you can see the bus here, but each board is, for its specific function is going to have its own connectors that are specific to the functionality of the board on the stack. So, as I mentioned, the PCI and the ISA bus were coexisting, and what I want to get to is the part where we get rid of the PCI, the ISA bus, and keep going here. I'm going to stop here, and we'll kind of take it from about here tomorrow, and we'll keep talking about the PC 104 standard.